So this is exercise astrophysics. Question 15 we did the last, and question 16. So in this question, as you can see here, the spectrum is given. The yellow line emitted by the helium discharge in the lab has a wavelength of 587.5 nanometers. The same line in the helium spectrum has a wavelength of 595.6 nanometers. So in the lab, like the same line in the helium spectrum of a star has measured. So this is in the lab. So in the lab, it is shorter wavelength, but it appears longer. It shows that this is moving away from us, because if the wavelength increase, it means it is moving away. If wavelength decrease, because wavelength increase means it is giving us a redshift. So we have to calculate the speed of a star relative to the Earth. So how we can work out? First, we'll work out the Doppler shift. So Doppler shift is change in wavelength over original wavelength, which is Z. So Z is equals to change in wavelength over original wavelength. So when we calculate a change or a difference, so it will be 595.6 minus 587.5 divided by original wavelength, means the wavelength which is emitted, we recorded in the lab. That is like from a stationary source, what wavelength we may recorded, that is the original wavelength. So 587.5, because all units are nano, so that's why I don't have to substitute exponent -9. I'll get the same answer. When you take a difference and then divide, this will give us a redshift. And then we have the formula that redshift is equals to speed at which the galaxies or stars are moving divided by speed of a light. So then Doppler shift, like this is a Doppler shift Z. And if Z is multiplied by speed of light, which is 3 exponent 8, we'll get the speed at which this galaxy is moving. And because the wavelength has increased, so this shows that this galaxy is moving away from us, if it or the star is moving away from us. Next is question 17. Explain how the light emitted from star enable us to determine the temperature of a star, hence its luminosity. So how the light emitted from the star enable us to determine the temperature and the luminosity, like how we know that what is the temperature of the star and what is the luminosity. So first, what we do, we record the spectrum of the star, and from that spectrum, we will work out the maximum wavelength. Because like when we collect the result, the spectrum, so the graph will be somewhat like this. And using this, the luminosity and the wavelength, so which one is the maximum wavelength? Maximum wavelength does not mean the highest wavelength. Lambda max. So first, what we do, we we record the spectrum of this star, like focusing on the star, and we'll find what is the highest wavelength, like wavelength, different wavelengths will be there from the star. We'll work out at what luminosity it has a maximum wavelength. That is called a lambda max. And we know lambda max, according to Wien's law, lambda max into temperature will give us 2.89 into 10⁻³ So we will, from its spectrum, we'll have lambda max. So from this lambda max, we can work out the temperature of a star. And how we work out the luminosity? So luminosity is like when we detect the spectrum, like observe this star. So we'll have the luminosity of this lambda max of the star, like collecting different wavelengths, and the wavelength which give us a maximum luminosity, that is we called as a lambda max. Or we can also use the HR diagram, Hertzsprung and Russell diagram, which is a relation between temperature and luminosity. So this is, rather than luminosity, this is usually intensity. So we can have a Hertzsprung Russell diagram, which is, say, like 10,000, 20,000 is there, 10,000 is there, 5,000, 2,500, and we have a luminosity compared to sun. So this will be the main sequence star. So after finding the temperature, if it is a main sequence star, after finding a temperature, we can work out its luminosity. So the points which you will mention. So first, we will record the spectrum of the star. After recording the spectrum, what we will do, we will, like, first we'll record the spectrum of the star, and we will determine the lambda max here. From the spectrum, we'll determine the lambda max. And then from lambda max, what we'll do, we'll use a Wien's law to find temperature. And after finding a temperature, use HZ, Hertzsprung and Russell diagram to find the luminosity. So here, Wien's law, temperature into lambda max will be equals to 2.89 into s power minus 3. That will give us temperature. And after knowing the temperature of the star will be there, and its luminosity compared to that of sun. If it's, but this can only be used for the main sequence star. Like our assumption is that this is a main sequence star. Because if it's not a main sequence star, we won't be able to identify its find it, because it won't follow the sequence, so we will not be able to find its luminosity. The next is an object whose luminosity is known, maybe refers to a standard candle. So stellar objects, the object which we know their luminosity, we call standard candle. Explain why standard candles are important to astronomers and outline how standard candles are used to find the distance of the star. So how we use the standard candle to determine, like, say this is a star which we focus on. So this star is emitting out radiation in all the directions. And what is the relation between the distance and the amount, the luminosity or intensity or a flux is equals to luminosity 4 pi d square. Like amount of the flux or amount of radiation we receive on unit area, which is a flux, that is inversely proportional to d square. If the distance of a star is double, the flux will decrease by 4. If a distance is 3 times, the flux will decrease by 9. So how a standard candle can be used to determine the distance of the star? So the idea is that the distance to a star, and this is usually used for distant object, like, because those stars which are very close to us, we can use a parallax, trigonometric parallax. But stars which are too far for the parallax, we can measure their brightness or a flux. And we know flux is inversely proportional to distance square. So we use this relation that F is equals to 4 pi, F is equals to luminosity, the power, 4 pi d square. So if I need d, the distance, so d square is equals to luminosity divided by 4 pi f. And if I need d, I will take a root. So d is equals to under root L divided by 4 pi f. So we have luminosity is already known, like, because when we say a standard candle, it means we know its luminosity. So luminosity is known. Flux we can calculate, we can measure the brightness or a flux or intensity that we can measure for the star. So that can be done. And there's 4 pi is constant, so we can determine at what distance this star is from us. So the main point of this standard candle, that we say we know the star is having a known luminosity. So when it has a known luminosity, we can use this relation, and normally it is used for the objects, the stellar objects which are too far from us. Which, if it is very close, then simply we can use a trigonometric parallax. Is it clear?